Hello again. In this video, I'm going to go over section 2.5, part 4. And what we're going to do in this section is we're going to continue to look at the end behavior of rational functions like we did in the last video. But in this case, we're going to look at a special case where the end behavior for the rational function results in having slant asymptotes. Okay, so let's look at this function here and find its end behavior. Now remember, the end behavior of this function is essentially what the y value of this function is approaching as x heads towards infinity and negative infinity. So let's look at the limit as x heads towards infinity first. Now remember, for these rational functions, initially you're going to get infinity over infinity, and so you have to change it to a determinable form, because infinity over infinity is an indeterminate form. And that's true if it's minus infinity over infinity as well. So let's change this to a determinable form, and the way we do that, if you remember, is we look at the bottom polynomial, which in this case is x plus 1, and so what we're going to do is we're going to multiply top and bottom of this rational function by 1 over x. Okay, so let's simplify this by distributing the 1 over x. So you get 2x squared over x plus 6x over x minus 2 over x. And then on the bottom, you get x over x plus 1 over x. Okay, and then of course this simplifies to 2x plus 6 minus 2 over x. And then on the bottom, you get 1 plus 1 over x. Okay, and then we're going to find the limit as x goes to infinity. Now, as x goes to infinity, remember these are heading towards 0. And so it looks like this on top, as x is getting bigger, this is getting larger as well, because you're getting 2 times a really big number plus 6, which is a really big number. And then on the bottom, it's getting closer to 1. So overall, this is heading towards positive infinity. So the end behavior on the right is that it's heading upward towards infinity. Okay, now if we redid all of this for x heading towards negative infinity, we would do the same thing and change it to this determinable form like this, with a slight difference at the very end, because now these are still heading towards 0 as x heads towards negative infinity, but this piece here is actually heading towards negative infinity because x is now negative. And so this number on top, this piece here, is heading towards negative infinity over 1, which is negative infinity. So the end behavior on the left is this function is heading downwards towards negative infinity. Okay, so we've discovered the end behavior of this rational function. Up on the right, down on the left. Great. So this is kind of what we did in the last video. But there's one small difference here. This is kind of a special case. So let me show you the graph of this function. So the graph of this function looks like this. So you can see as x is heading towards infinity, the y value is heading towards infinity. So the end behavior is up on the right and down on the left. But more specifically, so this is heading towards infinity, right? As x gets bigger. And this is heading towards minus infinity as x is getting smaller. But it's doing so in a very precise way, or we can define it a little more in detail as to how it's heading towards infinity. It's actually approaching this horizontal asymptote as it approaches infinity and negative infinity. So we're going to be a little bit more precise about how it's approaching infinity on the right and negative infinity on the left. It's actually approaching this slant asymptote. And so what we're going to do is we're actually going to find the slant asymptote that it's approaching. Okay, so how do you do that? Well, what you do to find the slant asymptote is you actually divide this rational function out using long division. Okay, so I'm going to go ahead and do that. Let's start with 2x squared plus 6x minus 2. And then using long division, we're going to divide that by x plus 1. Now, the way you do this, perform long division, is you take this first term here and you divide it by the first term here. So 2x squared divided by x is 2x. And that tells you what you're going to multiply by up here. So you're going to take this 2x and you're going to multiply it by x plus 1. Okay, and so let's see what you get. Just distribute here and you get 2x squared plus 2x. And then you have to subtract this entire thing. So I'm going to put that in parentheses and subtract it off. Okay, now of course that means I have to distribute this minus sign. So I'm going to go ahead and do that. So when you distribute the minus sign, this will become a negative and this will become a negative. Okay, now if you've done this correctly, then these should cancel out. This very first term should cancel out. That was the whole point in multiplying by 2x. Because I multiplied by 2x, I ended up getting 2x squared, and then I'm subtracting that off, so it should cancel with the 2x squared I had here. Okay, so then we're left with 4x here minus 2. And then I'm going to do this again. So then I'm going to take this 4x, the first term here, and divide it by the first term here. And of course that's equal to 4. So now I need to multiply by 4. And when I multiply this by 4, I get 4x plus 4. And I'm going to subtract that off. And of course that means you have to distribute this minus sign. So both of these become negatives. And then, of course, these end up canceling out as they should. And you're left with negative 6, which is your remainder. But technically, this remainder is still being divided by the divisor. So if you want to be very picky about how you write this, the final answer is negative 6 divided by x plus 1. So this is what you get when you divide this polynomial by this polynomial. It does not come out evenly. Okay, you're left with 2x plus 4 minus this fractional piece. Okay, so having said that, how does this help us? Well, this is how it helps. If I go back and evaluate this limit as x heads towards infinity, and then also we'll do it as x heads towards negative infinity. If I had just done this first, the limit of this function as x heads towards infinity is the same as the limit of this function as x heads towards infinity, since those two functions are equal. Okay, so I'm just going to figure out the limit of the function on the right-hand side. Okay, all right, well look, I think it's pretty clear that this piece is heading towards 0, since x is getting larger and larger. So it's like 2x plus 4 minus a really small number. So it looks like this is getting closer to 2x plus 4 if you want to be very specific about what it's approaching. Now, I agree. You could say that this is heading towards infinity minus a number that's getting closer to 0, which means this is heading towards infinity. That is a macroscopic view of what's happening. But if you want a very detailed, precise view of what's happening, more specifically, it's actually it's getting closer to 2x plus 4 minus a really small number. In other words, it's getting closer to 2x plus 4. Now, as this happens, x is getting larger and larger. Okay, so when x is 10, this is getting closer to 24. 100, it's getting closer to 204. 1,000, it's getting closer to 2,004, and so on. But as x is getting larger, it is getting closer to this number, 2x plus 4. But it's also heading towards infinity, right? Because as x goes to infinity, 2x plus 4 is heading towards infinity also. This is just a more specific, more precise, telling us exactly what the number is getting closer to, right? The specific value of the number that it actually is at any point for any x. Okay, so having said all that, I guess you would say as x is heading towards infinity, y is getting closer to 2x plus 4. And this is really a line, right? Y equals 2x plus 4 describes a line, and that is the slant asymptote. Okay, so going back to the graph, this line, 2x plus 4, that's the line that describes this slant asymptote. Okay? So that's a more specific understanding of the end behavior for this function. Not only is this heading towards infinity as x goes to infinity, but it's heading towards infinity in the sense that it's approaching this, or this slant asymptote at 2x plus 4. On both sides, right? On the left-hand side, this is heading towards minus infinity, but again, it's approaching this line, 2x plus 4, as it does that. Okay, so let me just mention, this is going to happen anytime the degree of the top polynomial is exactly one more than the degree of the bottom polynomial. So you can see that's the case here. The bottom of the degree of the bottom polynomial is 1, and the degree of the top polynomial is 2. So the top is exactly one more than the bottom. And that's when you're going to get a slant asymptote. Okay, so just to finish this off, Theorem 2.7 gives you a summary of the end behavior and the asymptotes that can occur for rational functions. So anytime you have a polynomial divided by another polynomial, you have a rational function. And they go ahead and write out the polynomials in general form. So p of x, the top polynomial, is being written in general form here. So it has degree m, and the leading coefficient is being described as a sub m. Whereas the bottom polynomial, q of x, has degree n, and the leading coefficient is being described as b sub n. Okay, so what this theorem says is if you have a rational function, in other words, a polynomial divided by another polynomial, if the degree of the top polynomial is smaller than the degree of the bottom polynomial, then the limit as x goes to plus or minus infinity of this rational function is 0. And therefore, y equals 0 is a horizontal asymptote. So anytime the degree of the top polynomial is smaller than the degree of the bottom polynomial, you know that the end behavior for this rational function is 0 on both sides. It's heading towards y equals 0. Okay, if the degrees of them are equal, if the degree of the top and the bottom are the same, m is equal to n, right? The degree of this one is equal to the degree of that one. Then the limit as x goes to plus or minus infinity of this rational function ends up being the leading coefficient of the top, a sub m, divided by the leading coefficient of the bottom polynomial, b sub n. And therefore, you have a horizontal asymptote at y is equal to a sub m divided by b sub n. If the degree of the top is bigger than the degree of the bottom, then this limit, as x goes to infinity or negative infinity, of this rational function is either infinity or negative infinity, and you have no horizontal asymptote in that case. And then if the degree of the top is one more than the degree of the bottom, then this limit is either infinity or negative infinity, and so you have no horizontal asymptote, but you do have a slant asymptote, and this is the case where the degree of the top is one more than the degree of the bottom. And then part E says, assuming that f of x is in reduced form, vertical asymptotes occur at the zeros of the q polynomial, q of x. And we've talked about this before in a previous video. If you want to find, this was about finding vertical asymptotes. If you want to find vertical asymptotes, what you have to do is you have to reduce this rational function to lowest terms and then set the bottom polynomial equal to 0 and then solve for x. And those are the zeros of the q sub x, the bottom polynomial. And wherever those zeros are, those are where you have vertical asymptotes. So this basically gives you an overall picture of what's going on with rational functions. It gives you the end behavior, and it tells you about the horizontal asymptotes, the slant asymptotes, and the vertical asymptotes. So it's a good reference. I would say anytime that you're working with rational functions and you want to know something about their asymptotes or their end behavior, you should refer back to this theorem. Okay, just to reinforce this theorem real quickly, in the previous video, we looked at these three different examples where we tried to find the end behavior of these rational functions. And so if you go back and look at the previous video, you can see the degree of the bottom is bigger here, right? Or the degree of the top is smaller than the bottom, right? The degree of the top is 1, the degree of the bottom is 2. So this is a case where it should head towards 0, and that's what we found. We found the end behavior for this to be 0. So there's a horizontal asymptote at y equals 0 for this one. Here, the degrees are the same, and so what's going to happen is it's going to head towards the leading coefficient divided by the leading coefficient. So 40 over 10, which is 4. And that's what happened in this case. And you get a horizontal asymptote at y equals 4. Okay, and then the last one that we looked at was this one, and you can see the degree of the top is bigger than the bottom. It's 3 on top and 1 on the bottom. And so this is a case where it's either going to head to infinity or negative infinity. And in this case, they both headed towards infinity on the left and the right. And of course, if that happens, you don't get a horizontal asymptote. And you don't, but you might get a slant asymptote, but the only time you get a slant asymptote is if the degree is bigger by 1 on the top. Exactly 1. In this case, it's bigger by 2. And so this didn't result in a slant asymptote. Okay, whereas this one did. Okay, because the degree of this one was bigger by 1. Okay, so I think this is a useful theorem to refer to anytime you're working with rational functions and their end behavior and their asymptotes. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.